Alright, hi, I'm Jackson.
And I'm Josh.
And this is Enigma Explained. Alright, so in the last video we talked a little bit about the structure of the rotors and what they might be used for. Here we're going to go a little more in depth and explain how the rotors are set up within the machine. So what we know from the previous video is that there's a bunch of spaghetti inside of these rotors, electrical nonsense that translates stuff. We'll learn more about that later in one of Josh's videos. But basically what's important is that each rotor and each reflector implement a different permutation. And that's important for later, but for now let's explain how they sit together so that these permutations can be used in the future. So what we're going to have is a series of rotors. So we're going to have rotors numbered 1 through n. And the way it's going to work is our first rotor is always going to be what's called a reflector. So the reflector, what's going to happen is the signal is going to come into one side of the reflector and it's always going to come back out the other side. And this is important because when we send a signal in after hitting a button, it's going to go into this series of rotors, go through all of the permutations, hit the reflector, and send it back out so that it'll light up the correct letter. So that's what the reflector is for. It has 26 different configurations it can be placed in, just like letters of the alphabet. But remember that the circuits or the signals go in one side and they come back out the same side. After that, we have up to n-1 other rotors, where n is our rightmost rotor. So, all these other rotors are basically going to be similar, except when signals come in one side, they get scrambled and come out the other side. And then when they come in the other side, they come out the first side. So this is basically the core of Enigma. How it works is signals come in one side, they go through the spaghetti, they hit the reflector, they come back through the spaghetti, and then they turn into different letters. So what we're going to do here is we're going to use n as our configuration parameter here for telling us how many rotors we're going to use. And the other Enigma machines, it was only up to 5 rotors, I believe, including the reflector, but we're better than that. We're going to do a lot more. So what's going to happen is each of these rotors that we discussed earlier, they have their ratchets, they have their alphabet rings, and the question is how does it all fit together? So what we're going to do is we're going to look over to this drawing, and let's pretend we're back in the old days, World War II. We only have 5 of these rotors, so let's call n equal to 5. So here's a drawing of the highest rotors that we have, and then we can assume that there are 2 more rotors over here where number 1 is the reflector. And so the way these things are going to fit together is you're going to have the nth rotor, the 5th in this case, be located on the right. So the very far right is going to be the nth rotor, and the very far left is going to be the first rotor. So always keep that in mind when you're going through this. What's important is that because the nth rotor is on the right, its ratchet is always uncovered. Remember, the alphabet ring covers the ratchet in such a way that the pawl cannot engage with the ratchet and turn the ring, or turn the rotor itself. So what we have here is a series of pawls which are in charge of turning these rotors themselves, but the 5th one in this case is always accessible to a pawl. So what's going to happen is anytime I hit a letter, all the pawls turn. And so anytime all the pawls turn, all the ratchets that are available will get engaged with the pawls and will turn. Now the 5th rotor is always available. So the 5th rotor is what we call the fast rotor. It will always turn every time you press a key. And that's kind of a useful thing so that the rest of the machine can always have a different permutation. So because the right ratchet is always uncovered, it will always turn. Now, aside from the the highest numbered rotor, there's going to be all the other ones, right? And what's different about them is that the alphabet ring from higher numbered rotors is going to cover the ratchet. So what this means is that the pawl only has access to the ratchet at certain times. And that certain time is going to be when there's a notch cut into this alphabet ring. And that notch is going to be maybe once or twice in the entire alphabet. There's usually 1 notch, maybe 2. But what's going to happen is this pawl can't actually turn this n-1, n-2, etc. rotor unless there's a notch in the rotor before it. So 4 cannot be turned unless 5 has a notch in the appropriate location for the pawl to access it. If it is there, 4 is able to turn, 5 is able to turn because it's uncovered. And again, so on. 3 can only turn if 4 has a notch in the right spot, and all the way down. Now, what we're also going to have is only certain rotors are going to be able to turn. Our reflector is never going to be able to turn, and we guarantee this by not putting a pawl in front of our reflector. So our reflector isn't going to have something that can turn it. So it'll always stay in the same location, and it's never going to like twist around or change which setting it's on. It's always going to stay in its position. In addition to the reflector not moving, we're going to have some number of non-moving rotors, and the way we guarantee that, again, is we don't have a pole. So if these were the only 3 poles I had here, and I had 5 rotors in place, then we would have 3 rotating rotors, moving rotors, because there's a pole that has access to 5, a pole that has access to 4, and a pole that has access to 3. Assuming that there are more rotors over here and there's no other poles, 2 is actually never going to turn. Even when 3's notch is available, there's nothing that can engage 2's ratchet and turn it, which means 2 will never change its setting. So basically, 5 can change, 4 can change, 3 can change, 2 and 1 will never change their setting over the course of this encryption. So yeah, that seems like a good explanation for now. We'll get into it in a little more detail